Hello everyone, welcome back to my YouTube channel Unfog with Dr. Atahar Parveen. In this session we are going to discuss solid state, and I have planned for this chapter a free class based on HSTR chemistry syllabus. Now according to the syllabus we need to know about crystal lattice, FCC, BCC and cubic structures. Before starting this class, I want to request you all that if you are free now, then only you watch this class, okay? If you are in hurry, you will not understand anything from this class, okay? So make time whenever you are free, then only try to watch this class, because this class requires lot of concentration and imagination while you are watching this class, okay? As we all know, matter, the substance that makes up everything around us, can exist in three primary states: solid, liquid and gas. And these states of matter are determined by the arrangement of molecules in them and the level of energy which is present in the substance. In this, solids have a fixed shape and volume because their molecules are tightly packed and they have a very little room to move. Whereas liquids, they have a fixed volume but they take the shape of their container because their molecules are close together but they have more freedom to move. Finally, talking about gases, they have neither a fixed shape nor volume because their molecules are far apart and they move rapidly, which spread and fill if there is any space available there. So these are the three states of matter: solid, liquid and gas. In this class, we will be dealing with solid state. So solids are characterized by their definite shape and volume, and they are having high density and they are incompressible. Incompressible means even if you try to press them, you cannot press it. Okay. So solids are hard, you can say. Now based on the arrangement of constituent particles, solids are classified into two types: crystalline solids and amorphous solids. Talking about crystalline solid state, they are those that have a typical geometry and there is a definite arrangement of particles in them. Now these particles can be atoms, molecules or ions, and this arrangement is done throughout the three-dimensional network of a crystal, that too in a long range order. Means the interaction between those particles is present even if the particles are far away from each other. Now example for crystalline solids are typically sodium chloride, NaCl, quartz and diamond. Now it's important for us to know about the crystal lattice when we discuss about crystalline solid state. So the crystal lattice is nothing but this symmetrical three-dimensional structural arrangement. Now this arrangement we are talking is about atoms, ions or molecules. Now this arrangement is inside a crystalline solid. Now this atoms, ions or molecules, we are treating them as points. So you can see here that there is a cube and there are atoms at the corners of that cube. Okay, and the distance between two atoms, you can decide them in the directions. That means it can be x direction, it can be y direction or it can be z direction. Okay. Now for instance, we give names as A, B, C for distance between two atoms. Now the distance between two atoms in x direction, you call it as A, and the distance between two atoms in y direction, you can call it as B, and distance between two atoms in z direction, you call it as C. Usually we call this A, B and C as a lattice parameters. Okay, A, B and C are lattice parameters. And the angle between atoms, you call that angles as alpha, beta and gamma. That also you decide with x, y and z direction. For example, the angle between x-axis and y-axis, you can call it as gamma. And the angle between y-axis and z-axis, you can call it as alpha. Angle between x-axis and z-axis, you can call it as beta. Basically, the angle between the atoms at the corners of that cube, you call it as alpha, beta or gamma. Okay. So, you are clear with the parameters of this cube, right? Alpha, beta, gamma and A, B, C. Okay. So, we will discuss about this in the later part of this class. Okay. Now, we will stop discussing about crystal lattice here and we will discuss other things like properties of crystalline solids. So, crystalline solids are having sharp melting point and they start melting when one particular temperature is reached. Okay. As I already told you, crystalline solids, they have typical arrangement of particles and they show cleavage property. Cleavage property means when you cut that crystalline solids with the edge of some sharp tool or something, then they will split into two pieces and the newly generated surfaces, they will be very smooth and plain. There will not be any rough surface if you cut that crystalline solids. Okay. So, that is the speciality of crystalline solids, that they show cleavage property. And also, they have definite heat of fusion. Heat of fusion means it is the amount of energy which is required to melt the given mass of solid at its particular melting point. Okay. So, they are having one definite heat of fusion. So, you will be knowing at what temperature that particular given crystalline solid will melt. Okay. And another speciality of crystalline solids is that they are anisotropic. Anisotropic means their physical properties, like for example, we have electrical resistance or refractive index. These type of physical properties, they show different values when you measure along different directions in the same crystal. Now, what are the different directions? I told you, right? X, Y and Z axis. When you measure these physical properties in different directions, you will find these physical properties to be slightly different. That's why you say that crystalline solids are anisotropic. Okay, very important point. They can ask it as a multiple choice question. Okay. And of course, we can say that crystalline solids are true solids. Okay. Now, on the basis of the nature of intermolecular forces or on the basis of nature of chemical bonding, crystalline solids can be further classified into four categories: molecular solids, ionic solids, metallic solids and covalent solids. Okay, molecular solids, ionic solids, metallic solids and covalent solids. I have the examples based on these different type of solids. First, we will know the examples so that we will get some rough idea about what type of solids we are talking about. After discussing about the examples, we will go in detail about all four types of solids. Okay. So, talking about ionic solids, compounds of metal cations and non-metal ions like sodium chloride or aluminum oxide or iron sulfide. These are examples of ionic solids. Then talking about metallic solids, metal atoms like aluminium, iron, chromium, that type of metal atoms are examples for metallic solids. For covalent network solids, you can say that carbon, metalloids and compounds of metalloids like silicon dioxide, okay, and all other compounds of carbon, they are all exhibiting certain type of network. So, they are called as covalent solids or network solids. Okay. Next, we have molecular solids. Examples for molecular solids include compounds of non-metals. Like for example, we have this phosphorus pentoxide is there, or we have this water, or we have this glucose C6H12O6. So, all these compounds are examples for molecular solids. Now, let's discuss in detail. Now, these molecular solids, means the constituent particles in them are just molecules. Now these molecular solids are further divided into three categories: non-polar molecular solids, polar molecular solids, and hydrogen bonded molecular solids. Talking about non-polar molecular solids, these solids are formed from molecules or atoms which share a non-polar covalent bond, and the atoms or molecules are held by weak dispersion force in these type of solids. Now this weak dispersion force are commonly known as London forces. And the physical nature of non-polar solids means that they are soft. Okay, they are not hard, they are soft, and they don't conduct electricity, so we can call them as insulators. Okay, basically non-polar molecular solids are soft and they are insulators, and they are having very low melting point. What are the examples of non-polar molecular solids? Hydrogen gas, chlorine gas, and iodine, etc. These type of molecular compounds, you can call them as non-polar molecular solids. Okay. Now talking about polar molecular solids, in these solids the molecules are held together by polar covalent bonds, and the atoms or molecules, they are bonded by what we call as van der Waals interactions. Of course, these are also weak interactions only, but when you compare it with London forces, these are little more stronger. Okay, and the physical nature is soft, and most of these are gases or liquids that we are talking about at room temperature. And these polar molecular solids also do not conduct electricity, and they have higher melting point when you compare with the non-polar molecular solids. Now examples of polar molecular solids are hydrogen chloride, sulfur dioxide, and ammonia, etc. Okay. Now talking about hydrogen bonded molecular solids. Now these solids contain polar covalent bonds with hydrogen, fluorine, oxygen, and nitrogen atoms. And molecules are held together through some strong hydrogen bonding here. Okay, and because they are held together with strong hydrogen bonding, it is obvious that their physical nature is very hard. I mean to say, these solids will be very hard, right? Because a strong hydrogen bonding is there. And of course, even these solids do not conduct electricity, and the speciality of these solids is that they are appearing, or you can say that their physical state is that they are volatile liquids or soft solids under room temperature. Now what are volatile liquids? See, solids means don't only imagine that it should be like a brick only, or it should be like ice only. Okay, so these are also solids which are having a physical state of a volatile liquid. Means these type of materials, they evaporate easily at a normal temperature. Basically, they will transform easily into vapor phase. Okay, so that's the reason why we are calling them as volatile liquids, because these type of materials, they will very easily transform into vapor phase. Okay, or also they can be some soft solids also. Okay, and that's the reason why we can say that they are having low melting point. Okay, the best example will be water, H2O, that in the form of ice. Okay. Now let's talk about the next type of solids, the ionic solids. In ionic solids, obviously as the name only suggests, the constituent particles will be ions, right? And these solids are formed by arrangement of cations and anions by some strong Coulombic forces. Okay. Now what is this Coulomb force? Coulomb force is always there between either positive and negative charges, or between positive charges, or between negative charges. Basically, this force is present between the ions, means the atoms which are having charges. Okay. And what is the force of that Coulomb interaction? I mean to say, what is the value of that Coulombic force between the cation and anion? It will be K into Q1 into Q2 upon R square, where Q1 will be the charge of one ion, Q2 will be the charge of another ion, and R will be the distance between these two ions. Okay, and K is the Coulomb constant. Okay, basically this Coulomb force is directly proportional to the product of the two ions, I mean to say charge of those two ions, and it will be inversely proportional to the square of the distance between those two ions. Okay. Now coming back to ionic solids, they are hard and brittle in nature and they act as an insulator in a solid state, but they can be conductors in a molten and aqueous state. Okay. So this is the speciality of ionic compounds, you can say. I mean to say ionic solids. Okay. So they are acting as insulators in solid state and they are acting as conductors in molten state. Okay. And also because they are held with a strong Coulomb force, we can say that they will be having very high melting point. Okay. Now basic examples for ionic solids include sodium chloride, magnesium oxide, zinc sulfide, or calcium fluoride, etc. Okay. Now talking about metallic solids. Now in metallic solids, positive metal ions are present in a sea of electrons. Now that electrons are also delocalized. Delocalized means they are not stable. They are not standing in one place. Okay. So these electrons are evenly spreading out throughout the crystal. And because of the presence of these free and mobile electrons, these electrons are responsible for high electrical conductivity and very high thermal conductivity. Okay. That's the reason why these solids are metals. So what are metals? Basically they are conductors. Either they are in solid state or they are in molten state. They are conductors. And what is the reason for this conduction? The reason is the presence of free and mobile electrons. And when electrons are present means of course they are carrying charges, and they are free means charge is moving. Charge is moving means conductivity is there. Okay. And talking about the physical nature of these solids, they are hard but they are malleable and ductile. Means they can be made into thin sheets and thin wires. Okay. And metallic solids are having high melting point when you compare with ionic solids. And what are the examples for metallic solids? Iron is there, copper is there, silver is there, magnesium is there. Okay. So all these type of atoms, they all belong to metallic solids. Okay. Now let's talk about covalent solids or network solids. Actually, a wide range of crystalline solids of non-metal form this covalent bonding between adjacent atoms in the entire of the crystal, and they form one giant molecule, or you can say that they are forming one large molecule. Among all these solids, covalent or network solids are special because these solids are as hard like diamond and soft like graphite. Okay. Now this diamond and graphite, they both are isotopes of carbon. Okay. And these solids are insulators. For example, we have diamond, but in case of graphite, it is conducting because there are free electrons present in that material. Okay. So you can say that diamond is an insulator, but graphite is a conductor which conducts electricity. So both the things are belonging to covalent or network solids only, and they are isotopes of carbon only. Okay. Now I am showing you here the cage of this graphite. It is actually graphite structure. You can see that three-dimensional picture of that graphite structure here. How atoms are placed in the corners of a hexagon here. Okay. So this is the example of a covalent solid. Okay. You have to remember this very important point, that diamond and graphite are examples of covalent or network solids. Okay. And not only that, you have more examples like boron is there, boron nitride is there, rhenium diborate is there, silicon carbide, silicon, germanium. All these are covalent network solids. Okay. Actually, they play the role like a metal, but they are having non-metallic elements in them. Clear, right? Okay. Now let's talk about other type of a solid state. Till now we were talking about crystalline solid state. Now we will discuss what is amorphous solid state. Now amorphous solid state means it includes the solids which are having property of rigidity and incompressibility, but that is not to a maximum extent. Okay, they are not as hard as crystalline solids. Okay, when you compare, these are having less rigidity and they are having less incompressibility. Okay, basically they are not having definite geometrical form or long range order like crystalline solids. Okay, examples are glass, rubber, plastic, etc. Now talking about properties of amorphous solids, they are gradually softened over range of temperature and they can be molded into different shapes of necessity. I mean to say you can mold them into different shapes on heating. Okay, best example is glass, even rubber also. Okay, and amorphous solids, you cannot call them as true solids. We were calling crystalline solids as true solids, right? We cannot call amorphous solids as the true solids. We call them as pseudo solids. Pseudo means false. Okay, either you call them as pseudo solids or you call them as a super cooled liquids, which means that they are having tendency to flow very slowly. Very slowly they will be flowing. Okay. Few more properties of amorphous solids are that they are having irregular shape. That is, their constituent particles, they are not having definite geometrical arrangement. And when you cut these amorphous solids with some sharp edge tool, you will observe some irregular surfaces when you cut them into two. Okay. Whereas in crystalline solids, we have seen that when we cut them into two, you can find the plane surfaces. Only condition is that you have to cut them with some sharp edge tool. Okay. And crystalline solids had definite heat of fusion, right? But amorphous solids are not having definite heat of fusion. That is because of their irregular arrangement of particles in them. Okay. And also amorphous solids are isotropic. What we told about crystalline solids, we told that they are anisotropic. That means their physical property would change from different directions. But that is not happening here. From whatever direction you measure the physical property, the physical property will be same. Okay. So you can say that amorphous solids are isotropic. And all this is happening because of irregular arrangement of particles in them. Okay. Amorphous solids have one of the very important use, that is amorphous silicon is there. No? It is one of the best photovoltaic material. Means it will be converting sunlight into electricity. So we can save energy, right? So sunlight is present in abundant, right? It will never exhaust, correct? So it is inexhaustible resource, right? So we can convert sunlight into electricity. So that is one of the important use of amorphous solid, that is a silicon. Okay. Now let's start discussing about crystal lattice again. Now the crystal lattice is the symmetrical three-dimensional structural arrangement of particles present in that solid. Those particles can be atoms, ions or molecules, whatever are present in that crystalline solid. They will be playing the role of the points. Here you can see the structure where these atoms or ions or molecules are present at the corners of the cubes. Okay, so they are geometrically arranged. So this geometrical arrangement of atoms, ions or molecules of the crystalline solid as points in space is known as crystal lattice. What are the characteristics of this crystal lattice? In a crystal lattice, each atom, molecule or ions, they are represented by single point, and these points are called lattice site or lattice point. And when you join these lattice sites or points together, you will find straight lines in a crystal lattice. And when you connect these straight lines, you get a three-dimensional view of a structure. I have shown you the pictures also. I will be showing again in this class. Again, more pictures I will be showing you. I will give you the 3D figures also. Okay. Now, this 3D arrangement is called crystal lattice, or it is also known as Bravais lattice. Remember this. Okay. Crystal lattice, or it is also known as Bravais lattice. Okay. Now, if you are not able to imagine whatever I am telling, You can just imagine this salt, rock salt will be there, no? Mota namak we call, no, in Hindi, rock salt. I am not talking about the powder salt. The other one, that rock salt will be there, no? So that is also a crystalline solid only. Okay, that is what we call as NaCl, right? So even in that also, that is, I think that is also a cubic structure. So even in that also, the atoms are placed like that in the corners. Okay. So this is, I think, a common layman language. You can just imagine this rock salt. Okay. Now coming to the actual topic of this chapter. The smallest repeating unit of this crystal lattice is known as the unit cell. Unit cell means, you can see the picture here in this diagram. The blue color shaded one cube box is there. No, that one cube box is known as unit cell. Okay. Now, all together, grouping all those unit cells, we are getting this crystal lattice. Okay. So, the smallest repeating unit of the crystal lattice is the unit cell, which will be the building block of a crystal. Clear, right? Of course, these unit cells are all identical and they are defined in such a way that they will fill the space without getting overlapped with each other. And the 3D arrangement of atoms or molecules or ions inside the crystal is called a crystal lattice, and it is made up of numerous unit cells. Okay. One of the three constituent particles, that means ions, molecules or atoms, they take up every lattice point in that crystal lattice. Okay. Now all this we are talking about is about close packing in solids. So solids are closely packed in such a manner that you cannot easily break them, and this is the strategy how these solids are packed. Okay. So we call that strategy or the style of packing as a close packing in solids. Now, packing of particles in solids arrangements can be of many types. Now, in this syllabus, we are having only three types: simple cubic, body-centered cubic, and face-centered cubic. Simple cubic, body-centered cubic means BCC, face-centered cubic means FCC. Okay, these are the type of arrangements with which the solids are packed closely. Okay. So here you can see how they are packed. This is the arrangement of particles in a solid. Okay. So they are packed in such a close manner that the bonding becomes very strong, and that's the reason why they are not easily breakable. And you can also see that each thing is similar to other thing. So all the unit cells are similar to each other. Okay. There is no change at all. We also call it as periodicity actually. Okay, periodicity. Now, as I was talking about this simple cubic, body-centered cubic and face-centered cubic, now these are types of unit cell. Okay, actually there are few other types of unit cells also, but we are talking about these three basic types of unit cells. Okay, simple cubic, body-centered cubic, BCC, and FCC, face-centered cubic. Let's discuss about each type in a clear manner now. Okay. Simple cubic unit cell. Here the atoms are present only at the corners. You can see how the atoms are present only at the corners. Now when I talk about simple cubic unit cell, you can imagine one cube, one three-dimensional cube, one box you can say. Okay, I am giving you the 3D figure also so that you can imagine. So here the atoms are present only at the corners. Now, how many corners does a cube have? A cube is having 8 corners. You can count it. Okay. Now, every atom at corner is taking its place. So, there will be 8 atoms at 8 corners, right? Now, the twist is every atom at the corner is shared among 8 adjacent unit cells. So, this is very interesting. See. This unit cell is made up of 8 atoms which are present at the corner, but each atom is shared by 8 neighboring unit cells. You can see the 3D figure here and try to imagine. So there are 4 unit cells, you can see in the figure here. There are 4 unit cells in the same layer and there are 4 in the upper or lower layer. Basically there are 8 unit cells, right? 4 up, 4 down. So therefore a particular unit cell will be having only 1/8 of each atom. Correct? 1/8 of each atom will be belonging to that unit cell. So in each cubic unit cell, there are 8 atoms at the corners. So how many number of atoms will be present in one unit cell then? 8 into 1/8. So one unit cell will have only one full atom. Okay? See, try to imagine what I am telling. Now here in this diagram, you can see that 4 green unit cells are there upper and 4 green unit cells are below, right? So imagine that all unit cells are having atoms at their corner. Okay? So that one atom will be shared by 8 unit cells. Then you can imagine that how many number of atoms will belong to one particular unit cell, means it will be 1/8 into 8. So one unit cell will have its own atom. Number of atoms will be only 1. Okay. Don't worry if you are not understanding. I will show you more 3D diagrams so that you will be understanding it in a better manner. Okay. So these are the structures. I think here you can understand it in a better manner. See, the figure number A is the open structure of this cubic cell. Now this atoms, if you imagine them as bigger atoms, so that your cube will get closed with that atoms. In figure B, you can see that it is a space filling structure. And in figure C, you can see the actual portion of atoms which is belonging to one unit cell. See, 1/8 plus 1/8 plus 1/8, like that you have to do 8 times. You will get one atom. Okay. 1/8 plus 1/8 plus 1/8 till 8 times if you do, you will get 8/8. 8 will get cancelled and you will get one atom for one unit cell. Okay. In this simple cubic unit cell. Okay. Now let's talk about a body-centered cubic unit cell, means BCC structure. Now this is having atoms at each corner of the cube like the simple cubic thing, but one extra atom will be there at the center of the structure. It is similar to simple cubic, but one extra atom is present at the center of the structure. Now this diagram which is shown below, it is called as open structure. And according to this structure, atom of the body center will be wholly belonging to the unit cell. Correct? So inside the unit cell it is in between the box. Okay, in middle of the box it is present. Means no other unit cell will ask for this atom, right? So this atom is not shared by any other unit cell. It is wholly belonging to that particular unit cell. So we have that one atom here. And like a simple cubic, number of atoms in BCC also, we have 8 corners and 1/8 atoms will be there per corner atom. So together, if you talk about corner atoms, then the entire unit cell will have one more atom. Correct? 1/8 plus 1/8 plus 1/8, if I do it 8 times, I will get one atom. So one atom in the corner, and together all corner atoms, if I add up, I will get one atom. So how many total number of atoms will be present in BCC? It will be 2 atoms. Okay? Clear, right? See, here I am showing you this 3D figure. You can understand it in a better manner. You can imagine how I am telling that there are 2 atoms in this body-centered unit cell. Now also you can see how this is shared also. How the atoms are shared also you can see. See, together you will get one atom here. All 1/8, 1/8 together. You will get one atom and one atom is present in the center. Okay, clear, right? So total we have 2 atoms in this BCC unit cell. Okay. Now let's talk about FCC. face-centered cubic unit cell. This cell contains atoms at all corners of the crystal lattice like the previous ones, and there is no center atom. There is no atom in the between of the cube here. Here there are center atoms at the center of a face of each cube. See how many faces will be there for that cube box. One will be there in the top, one will be there in the bottom, and there will be adjacent 4, right? So every face is having one atom in the center of each face. Okay, I think you can imagine now. See, what I am telling is, at the corners though atoms are there, like previous two cells, no, like that only at corners atoms are there, but atoms are also present on each face of the cube. They are present at the center of each face of the cube. Okay, now imagine that atom which is present in the center of that face, it will be shared by the neighboring cell also, right? So how many cells will share that atom? Only 2 cells, right? Because it is on the face, it is not on the corner, it is on the face. Okay, so only 2 cubes together can stick together through one face. So the atom present at the face center is shared between 2 adjacent unit cells. Okay, so that's the reason why only half of each atom will belong to individual cell. Okay, now in FCC unit cell, atoms are present in all corners of the crystal lattice also. Okay, and also there is an atom present at the center of every face of the cube. Correct. So you can imagine here, in order to find the number of atoms belonging to one FCC unit cell, you can see here this 3D figure. See, together all 8 corners, one atom. Next to face also they are having present, their atoms are present. So how many faces will be there in a cube? There will be 6 faces, right? So each atom will play the role of a half atom for one face, right? So that means 6 by 2, right? So 3. So total atoms present in FCC should be 4. Okay, I will explain you. See, 8 corners into 1 by 8 per corner atom, that will give you 1 atom. How 6 face centered atoms, 6 are there, but half atom per unit cell, so it will be 3 atoms. So now this say 6 atoms into half, correct? So you will get 3 atoms. Now you have to add up, right? 1 atom plus 3 atoms will give you 4 atoms. So total number of atoms in FCC are 4 atoms. Okay, so same 3D thing I am showing it to you here again. Maybe you would like to imagine it again. You can see that there are 4 atoms here in FCC unit cell. Okay, you see how it is, the sharing is done. That is important here. See, this is 1, then these are 3. Total 4 particles per unit cell. Okay. Now, as we discussed about the cubic system, like that only we have few more which are not given in our syllabus. Okay, they are tetragonal, rhombohedral or trigonal, orthorhombic or rhombic, monoclinic, triclinic, hexagonal. I have the pictures also. So we have been discussing only about cubic structure in this class. Okay, so the speciality of cubic structure is that all the interatomic distances A, B and C, they are equal to each other, because we are talking about a cube, right? Cube is made up of square, right? So square faces will be there for cube. So everything should be same only, and angles also should be 90 degree. Correct. So we have been discussing only about cube because only that is given in our syllabus. Rest things also I am giving you just in case you are interested to learn. I will just tell you roughly. In this, if you see orthorhombic thing, A, B, C are not equal, but angles alpha, beta, gamma are 90 degree. Okay. And if you talk about hexagonal, it is having hexagons. Hexagons means what will be the angle? It will be 120 degree, right? So one angle is 120 degree, other 2 angles are 90 degree, and A, B is equal to each other, but they are not equal to C. Okay. Like that only if you see monoclinic, A, B, C are not equal to each other, and one angle is not equal to 90 degree. Okay. Whereas in tetragonal, all angles are 90 degree, only one side is not equal. I mean to say only C is not equal, A and B are equal to each other. Okay. In case you are interested, you learn. Anyway, this is not in our syllabus and this becomes a next level thing. Okay. One more thing, if you want, I'll give you another point also. See, we have this 7 crystal systems. No. Now these 7 crystal systems, if you if you classify them in a more elaborate manner, you can have 14 Breve lattice. How that 14 Breve lattice means? See, here I am talking about cube only, right? Cubic thing, no. But in cubic we have simple cubic, we have BCC, we have FCC, no. Like that only, if you classify in a more elaborate manner to other crystal systems, totally you will get 14 Breve lattice. Okay, clear, right? I have not written this point. If you are interested, you can just keep in your mind that Breve lattice number is 14 Breve lattice are there. Okay. Now, when we are talking about this crystal systems, we are telling that these are solids only, right? So, if they are solids means we need to know how nicely they are packed. Correct? So, that thing we call as packing efficiency. So, packing efficiency means nothing but volume of atoms in unit cell divided by total volume of unit cell. So, how much volume does the particular atom takes in that unit cell? You add them up. You add number of atoms and you multiply by the volume of each atom. That will be in your numerator, and total volume of unit cell, that will be in your denominator. When you take the ratio of these two things, you will get what we call as packing efficiency. Usually we address it in percentage only. Okay, packing efficiency, we address it in percentage. It is nothing but the fraction of total volume of unit cell that is occupied by atoms. Okay. Now talking about simple cubic, BCC and FCC, we know number of atoms at corners, we know number of atoms at centers, we know number of atoms at faces. Also we know number of atoms per unit cell now. Everything we have discussed. Now packing efficiency, I will not go into details about how we calculate it. Just in case they ask in examination, you remember the number. Okay, I will not go into detail. But if you are really interested, you can calculate. You have to find the volume of atom now. See, I will show it to you here. See, volume of one atom will be 4 by 3 pi r cube because atom is spherical in shape, right? So, volume of sphere is 4 by 3 pi r cube. Okay. Now, what is this r? R is the radius of the atom at the center of the cube. Okay. What is the radius of the atom? And that atom which is present in the center of the cube, now that radius we are taking. So, with that you can find the volume, correct? Now, A though we know it is the distance between two atoms, or it is the edge length of the cube, you can say. Okay. Now, we have a relation between this R and A. For simple cubic, R is equal to A by 2. For cubic, R is equal to A root 3 by 4. And for FCC, it is R is equal to A root 2 by 4. Okay. Actually, there is one mistake here. In the first block, no, it is only simple cubic. Okay. Simple cubic, it is R is equal to A by 2. For body centered cubic, R is equal to A root 3 by 4. For face centered cubic, R is equal to A into root 2 by 4. Okay, clear, right? Now you can easily calculate volume, right? We have the volume of a conventional cell. It is A cube. Okay, because it is a cube, right? What is the volume of a cube? It is A cube only. Correct. So you can find the volume of each unit cell by calculating the value of A. How you calculate the value of A? You can calculate the value of A by using the value of R. Okay. So that is how you do. But if you are interested, you go for calculation or just remember the formula, because these are all next level things. Okay. This all will be asked in pure recruitment things. Okay. Anyway, now till now we were talking about unit cell, right? There is something known as primitive cell also. Primitive cell is a little bit different from unit cell, because in a primitive cell, whether it is simple cubic, BCC or FCC, you will not have any atom in the center. Okay, they will be just, it is a small unit of crystal which when repeated in 3 dimensionals, no, it will form entire crystal structure. Okay, anyway, don't get into it, even that is not there in your syllabus. Only thing is, it just name, as name only indicates, primitive cell means it is a more simpler cell, you can say. Okay. Now, another point which I want to tell is about coordination number. Coordination number means number of atoms which are present as neighbors. Okay, in simple cubic you will get 6 coordination number, means one atom will have 6 atoms as its neighbors. Okay, like that only in body centered cubic or BCC you will have 8 atoms as its neighbors. Like that only in FCC you will have 12 atoms as neighbors for one atom. Okay, that is your coordination number. So you need to remember all these numbers because it's very important. Okay. Now let's discuss few multiple choice questions. First question. Which of the following exists as covalent crystals in solid state? It is silicon. We have discussed it, right? Next, in a face-centered cubic lattice, a unit cell is equally shaded by how many faces? It is 6. Okay. Which of the following is a network solid? It is a diamond thing. We have showed you the figure also, right? Next, this is HSTR 2015 question. Example of covalent crystalline solid. Of course, it should be SiO2. We have discussed it also. Next, dash is a crystalline's basic repetitive structural unit. Obviously, unit cell, right? So, it is made up of, crystalline solid is made up of numerous tiny crystals, each of which we call as a unit cell. Next, which of the following crystal structures has the highest packing efficiency? See, obviously the packing efficiency should be more for face-centered cubic cell, right? Why? Because number of atoms are more, right? So, number of atoms are more means volume also will be more, right? So, if the numerator is more means packing efficiency also will be more, right? Okay, I showed you the figure also. You have to remember 74%. Okay. See here, for FCC it is 74%, for BCC it is 68%, for simple cubic you just remember as 52%, okay. Either you remember it in increasing order or you remember it in decreasing order, it's up to you, okay. Simple cubic means less the number you can remember, 52%. Body centered cubic, BCC 68%, FCC 74%, you can take it as a trick also, cubic C, BCC, FCC, okay. So, cubic 52%, BCC 68%, FCC 74%. We are talking about packing fraction or packing efficiency. Okay. Next, which crystal structure has the lowest packing efficiency? Of course, it should be simple cubic 52%. Okay. Next, which crystal structure has the largest volume per atom? It should be FCC only. Correct. Next, volume of a cube with a side length of A is, it should be A cube. Okay. That is what is the volume for unit cell also, right? That's the reason, right? Unit cell is in the form of a cube and cube is having volume of A cube. That's why we are telling that the volume of the unit cell is A cube. Okay. Next question. If the side length of a simple cubic unit cell is A, what is the volume of the unit cell? Okay. I repeat, if the side length of a simple cubic unit cell is A, what is the volume of the unit cell? A square, A cube or 2A cube. Okay. So, I am not going to give the answer to this question. You have to comment me the answer for this question. Okay. Now, talking about a few examples which are exhibiting either simple cubic structure or BCC or FCC structure. Okay. To start with simple cubic structure, there are very less metals which exhibit this simple cubic structure, and usually they are having low melting points and they are soft metals. Okay. The best available example for simple cubic structure is polonium. Okay. You have to remember this, polonium. Examples are very important. Anything based on examples can be asked as MCQ in HSTR. Okay. Now talking about the BCC structures, they are also commonly found in metals like iron, tungsten, chromium and niobium, and these metals are typically hard and they are having high melting points. Okay, we were talking about metals exhibiting simple cubic as they are having low melting points, right? And they are soft, but in BCC structures the metals are typically hard and they have high melting points. Okay, now coming to the FCC structures, they are also found in metals only, but what type of metals? They are copper, aluminium, gold and silver. Basically, these are the metals which are typically soft and they have no melting points, and metals like copper, aluminium, gold and silver are exhibiting FCC. Okay. So one thing which we have to keep in our mind is non-metals, they generally do not form FCC structures. Okay. Even BCC and simple cubic also very few non-metals are there, or you can say that they are negligible. Okay. So this simple cubic, BCC and FCC structures are usually exhibited by metals only. Okay. And I have given you the names of those metals also here. Okay. Now, as I was telling you about the coordination number, I told you that there is one atom, and what are the neighbors of that atom? So many number of neighbors will be the coordination number for that particular structure, right? So here I am giving you a picture so that it will become easy for your imagination. I am giving you just a simple thing, this simple cubic thing. I am giving you coordination number. You can see here the atom which is at the center of this cube, it is having 6 nearest neighbors. So the numbers are also written 1, 2, 3, 4, 5, 6. So the nearest neighbors for that atoms are 6. Thus the reason why we say that the simple cubic crystal structure is having coordination number 6. Okay. We can also talk about the next nearest neighbor, but we don't need to discuss about all that. Okay, that becomes next level. Okay, even this is also next level, but I thought that at least you should have an idea about what is coordination number, right? That's the reason why I'm not giving you pictures of BCC and FCC. I don't want to scare you. Okay. Okay, friends. This finishes your chapter solid state from HSTR chemistry syllabus. So if you like this video, please click the like button. If you don't like the video, please click the unlike button, and please don't forget to share among other teacher recruitment examination aspirants. And if you have not subscribed to my channel, please subscribe to this channel. Okay. And also we have a Telegram channel. You can join the Telegram channel. We keep discussing things there. And also if you are interested to join in HSTR CB course, the details of the course are given in the description box below this video. Okay then. Thank you. All the best. Bye.